Hello, in this video I'll be talking about our CVPR 2021 paper, Patch Nebulad, Multi-Scale Fusion of Locally Global Descriptors for Place Recognition. In this paper, we deal with the visual place recognition problem. Say you have a query image recorded by a robot, and your objective is to work out where in the world you are based on that image. And all you have is a prior database of reference images to localize against. The visual place recognition problem often has to deal with challenging situations, such as appearance change, viewpoint change, and structural changes in the environment. This technique is commonly used as an initial image retrieval step before doing 6DoF pose estimation. In this work, we extend upon the original NetVLAD architecture. In NetVLAD, an input image is processed for a CNN, and a collection of NetVLAD residuals are computed. Each individual feature in feature space is compared to a corresponding learnt cluster center, and the residual between a feature and its cluster center is computed, and all residuals are aggregated. The residuals are aggregated over the entire width by height space of the feature maps to produce a single global descriptor. We propose Patch Nebulad. Patch Nebulad instead creates locally global descriptors from a collection of patches in the feature map. We start with the same backbone as NetVLAD, except in the VLAD space, we now aggregate over small patches in the input feature window. As you can see here, a patch will consist of a small section of the full feature map space, and each patch produces its own local descriptor. We demonstrate that patches can be produced at any arbitrary size, and we use an integral image technique for rapid aggregation of features. We found that the fusion of multiple different size patches yields the best recognition performance. We then perform image retrieval using a cross-matching of patches with a subsequent spatial verification scoring for highly accurate image retrieval. Our full pipeline involves using a global retrieval method such as NetVLAD to produce a top 100 candidate list. For each of those top 100 candidates, we collect a set of patches in feature space for both query and candidate, and for each patch, we produce our Patch Nebulad descriptor. These descriptors are then mutual nearest neighbor matched, and the mutual neighbors are then scored with a spatial verification algorithm. We include both RANSAC and our own fast spatial verification algorithm that's almost as good as RANSAC, but an order of magnitude faster. We then repeat this for the 3 different patch sizes, and then each of the patch sizes is fused with a weighting, a pre-learned weighting value, to produce a final multi-scale fusion image retrieval score, in order to re-rank the initial candidate list to be more accurate. So I'll move on to our summary results now. We tested our approach on a variety of benchmark datasets, encompassing a wide range of appearance and viewpoint changes. Our datasets include Norland, which is a train journey through Norland of about 700 kilometers, the Mapillary Streets dataset, recorded across a variety of cities in the world, Tokyo 24/7, which compares between images collected from a smartphone to Street View images with both viewpoint and appearance changes, and finally, the Robotcast Seasons and Extended CMU Seasons datasets that were used in the visual localization challenges. What we found is that Patch Nebulad performs either more accurately than the state-of-the-art or much faster than the state-of-the-art. We particularly excel when tight localization tolerances are required, as can be observed on the localization challenge datasets. This is an attribute that is particularly useful for place recognition. We compared against 2 state-of-the-art local descriptor and matching techniques, SuperGLUE and DELG, along with some global descriptor baselines. Now I'll show our compute speed comparisons. All configurations of Patch Nebulad operate faster than SuperGLUE or DELG. Our highest performing method, denoted by the red star, is much faster than DELG and slightly faster than SuperGLUE. We also contribute much faster configurations of Patch Nebulad, with smaller local descriptors that are significantly faster with our spatial verification algorithm. Our fastest configuration, denoted by the green triangle, only has a small reduction in recall while being 43 times faster than SuperGLUE and 430 times faster than DELG, with a localization latency of only 140 milliseconds per query image. Our work is available as open source on GitHub. Thank you for watching our presentation on Patch Nebulad.